Okay, this is 2.5 on infinite limits. I think we've already kind of covered this idea. We want to make it a little bit more exact now. There's actually a strict definition that'll go along with this, like a kind of like an epsilon delta thing. Um, yeah, sure. Let's dive in here. Here's problem one. And it's basically just a type of non-existent limit. So we talked about three types of failures of limits. Oscillation. When you have another type is when you have different left and right hand limits, and then the third type is unboundedness. Okay, so this is that third type. We just want to put a sort of a name on it, and we've sort of been fiddling around with it, but now we'll make it more exact. Okay. So anyways, here is the first problem in the book. F of x is 2 times the absolute value of x all over x squared minus 4. And we can look at it analytically. In particular, we'll want to know the limit of f of x as x approaches where the denominator is 0. Okay, so there's an asymptote there. And as you may expect, we're going to have an issue. All right, so as x approaches -2 of f of x, what's going on with this thing? So set up your table, and we'll want to approach -2 from either side. So it still is the matter if you had different kind of left and right hand limits, even though they're non-existent, you can't really put a label on it. So if you have one direction infinity, the other direction's negative infinity, you can't say somehow the limit is infinity. You can't put kind of a title on it. You can title the left and right hand limits, but not this like official limit. The only time you could put a name on it then, I think according to the book, is if they're both going in the same direction with unbounded behavior. So they both have to go to infinity for you to put a name on it, okay? In other words, this direction and this direction both have to go to infinity, or this direction and this direction both have to go to negative infinity. And when that happens, then you could say that this has some sort of limit. I mean, technically it doesn't exist, but we put a name on it. So anyways, you go to your idea of approaches. So here's -2 on the number line. We want to approach from that direction on this side and this direction on this side. So from this side, we'll be thinking of numbers like -2.1, -2.01, -2.001. And on the other side, you're thinking like -1.99 eventually, right? So this would be -1.9. Sort of going off the screen there. This is -1.99 and then -1.999. Okay. And then you just plop them into your calculator and kind of note the behavior. So this is 10.24. This one was 100.24. This one was 1,000.24. So it looks like from this direction, at least, it's going to negative infinity, or sorry, yeah, no, positive infinity, sorry. On the other side, then, the other side of the pond, 9.74, and then 99.75, and then 999.75, okay? So from this direction, it looks like it's also going to positive infinity. Okay, so at the end of the day, we'll say that this limit is positive infinity. We don't have to write the plus sign for positive. You just put infinity and it's assumed to be positive, okay? Ugh, that's my little marker. Okay. So we have a strict definition for this idea. Basically, something will go to infinity if for any value that you can imagine, I can find a value, an x value that's close to whatever point you're trying to approach, such that the value, when I the output of the function is bigger than the number that you imagine. Okay, so let's write that out. This is another strict definition. I won't worry too much more about this definition other than to just write it out. If you want to continue studying calculus, like on an advanced level, you would have to have these kind of definitions memorized and be fluent in them. But anyways, let f be a function defined at every real number in some open interval containing C, except possibly at that point C. So again, this is just a limit. We're not worried about what happens exactly at C. Then this new statement, limit as x goes to C of f of x equals infinity, means that for each value m greater than 0 that you can imagine, there'll exist a delta greater than 0 such that if your x value is within a delta distance of C, then the f of x value will be greater than this particular m value that you've created. Okay, and I should have a little greater than 0 there. Likewise, the statement with negative infinity in it. So we'll say likewise, the limit as x goes to C of f of x equals negative infinity means that for any, or for each n less than 0 that you can conjure, there'll exist a delta greater than 0 such that if your x value is within a delta distance of C, then your function value will be less than that n value that was given. Okay. Okay, so we'll just state that definition and then kind of move on from it. There are probably nice little pictures in the book, so you can imagine here is some value m that you're imagining, and then for any m that you imagine, there's going to be a delta value around our C such that for any x in that delta bubble, the output is going to be above m. Okay, so you can imagine the function going something like this maybe. So if I picked, I don't know, x value right here, obviously its output is greater than m. Okay. Okay. So, anyways, let's look at, graphically at playing around with this idea. Determine the limit graphically. Here's number 5. So we have the function f of x equals 1 over x minus 4. Okay, and we can graph this by hand quickly. If you just remind yourself that the rational function looks like this, y equals 1 over x. And then this guy is just a translated version over by 4 units. So this thing will look like the following: 1, 2, 3, 4. There's our new asymptote. So this thing has an asymptote at y equals, x equals 0. This guy has an asymptote at x equals 4. Okay. So we'll have our branches like this. The limit in either direction, so let's consider the limit as x approaches 4 from the negative side, this side. What's happening is that the y values are going to negative infinity, right? So for any n value you give me, I can find x or a delta such that if I pick any x value within delta of this 0.4, this function will be less than that n value that you provide. So anyways, the limit of f of x, it's going down, 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 down. So it's going to negative infinity. Okay? And then from the right, we have it going to where? Well, it's going up, 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 so that you'll consider that as positive infinity. And then the note that I was trying to make at the beginning of the lecture is that if you are considering both sides simultaneously, you can't really say it's going to positive infinity because this side's going to negative infinity. And likewise, you can't say it's going to negative infinity because this side's going to positive infinity. So in this case, you would just be forced to say the limit does not exist. Right? Okay. Theorem 2.14 then talks about vertical asymptotes, and you note here you have a vertical asymptote, particularly where the denominator is equal to 4. Okay, so according to Theorem 2.14, or looking at Theorem 2.14, we'll want to find vertical asymptotes, and these will be places where you have basically division by 0. So the numerator will be some constant, and the denominator will be 0. So let's look at finding vertical asymptotes. So find vertical asymptotes. If you want the rigorous definition, you can look at the definition on page 105. Okay. But basically, it's where you have a rational function, which is a quotient of 2 polynomials, and the numerator is some number L when you plug in C, and the denominator is 0. Okay, so that's what you're looking for. So let's look at number 14 and see how this goes. So I have f of x equals 2 all over x minus 3 squared. Right, so you're just going to take the denominator basically and set it equal to 0. So x minus 3 squared equals 0. That'll equal 0 where x minus 3 is equal to 0. And then you could solve by adding 3 to both sides. So you get x is 3 must be a vertical asymptote. Okay. So I'll just write VA at x equals 3. Let's look at 18. So we have h of s equals 3s plus 4 all over s squared minus 16. We could factor the denominator and, well, just set it equal to 0. Right, let's just cut to the chase, right? And then we could factor s minus 4 times s plus 4 is 0. And then, of course, s is 4, and then s is negative 4 are our vertical asymptotes. Okay, we want to be a little careful that the numerator is not simultaneously equal to 0, because in those cases it won't have an asymptote. So in that, with that regard, in that respect, let's look at number 20. We have g of x equals x cubed minus 8 all over x minus 2. Okay. You got to factor this guy. It's a difference of cubes. So we have this formula, the SOAP formula. It tells you how that you do the sign. So it's the same, and then the opposite sign, and then always positive, SOAP. Okay, S-O-A-P. So anyways, x minus 2, and then you get x squared, and then 2x, and then plus 4. And then downstairs, I have x minus 2. So my point is here that if you were to just blindly set x minus 2 equal to 0, you would suspect that the vertical asymptote is at x equals 2. But then if you go and factor it, you see that this is really a removable discontinuity, and it won't have an asymptote there. It's just going to have that hole that we discussed in a previous lecture. Okay? So it'll behave like this thing, and even on the approach. So if you were to take the limit as x goes to 2, it would be 4 plus 8 plus 4, right? So 16. There's no vertical asymptote there, and it's particular because this top value is not L, it's actually some 0. Okay, so L is not 0. All right, so anyways, here there's no vertical asymptote. Okay. One-sided limits again. So I guess we kind of already talked about this a little bit in the previous lecture, but anyways, the book will want you to mess around with this a bit. Find the one-sided limit. And in particular, we have 38. The limit as x goes to 1 from the left of negative 1 all over x minus 1 squared. Okay, so whenever you have this asymptote issue, your limit is going to go to either, your one-sided limit is either going to go to infinity or negative infinity, automatic. Okay, so it's almost like if you have like 2 seconds left on the exam and I'm walking around picking up your exam, I'm like, oh, you got to turn it in now. You could just write down infinity, and you got a 50-50 chance of being right. Okay, so the point is, note if you have a limit of something which behaves as some number over 0, it's going to either always be positive infinity or negative infinity. Okay. Oops. So one off the page there. Okay, well, let's make sure that it's the sign is correct. And to do that, you just do a test value as you approach 1, right? So we're approaching from which direction? We're approaching from the left here. So I need to pick something like 0.9. Okay, so I'll put like 0.9 in there. And that's really all you need. You just need 1 point to determine the sign of the infinity. You know it's an asymptote, so you know it's shooting off to infinity because you have this number all over 0. When you plug 1 into here, you get 1 minus 1, which is 0. Okay, so you have some number over 0. And you will definitely have positive or negative infinity. Okay, you just have to figure out which is which. So you do a test value, and that tells you the sign. Right, so I'll have negative 1 all over 0.1 minus 1 squared. Anything squared is positive, so this is going to be a negative divided by a positive, which will be negative. Okay? And then as soon as you get that, you can say, oh, that's the sign of the infinity. Okay. Let's do one more of those. So 39. They want to know the limit as x goes to 2 from the right of x over x minus 2. Okay, so if you plug 2 into this thing, you get 2 over 2 minus 2, which is, you get this type, L over 0. So automatically, again, you know it's either plus or minus infinity. You just have to figure out the sign on it. Okay. So what do? You go to your table. Let's look at the approach. Here's 2. I'm coming in from the right, so I want to consider something like 2.1. and all you need is the sign. Okay, so 2.1, and then if you plug 2.1 into here, you get a positive all over a positive, so this must be positive infinity, so I'll just leave it there. And they're really that easy. So some people make a big deal out of it, but I mean, it's just, it is this process. Okay, anyways, when you're dealing with infinite limits, there's all these infinite limit laws. You'll sort of, if you study limits in more detail, you'll kind of want to classify all the different types of limits. So infinite limit laws. Here we're looking at one limit going to infinity. So we have limit of f of x equals infinity, and then the limit of this other guy is going to some constant number, okay, where L is, I believe they want it to be positive. Okay, so the first one says that if you add in a constant to something that's going to infinity, it'll still go to infinity. It doesn't make a difference, okay? So the limit as x goes to whatever number of f of x plus or minus g of x, you can kind of just completely disregard this thing. It's not going to make a difference because it's going to be, like if you looked at a table, this thing would be like 100, this would be 1. You know, and then this would be 1,000, this would be 1, and then this would be 10,000, this would be 1. So at each point you're getting like 101, 1,001, 10,001, 100,001. It's still going to go to infinity, regardless of what you're adding in on top of it. Okay, even if you were subtracting by 1, that would be 999, 999. Okay, so it still go there. If you multiply, it'll have the same effect. I mean, it's not going to mess with this thing going to infinity. You know, instead of going 100, 1,000, 10,000, you're going to have 100 times this thing. So maybe this thing is going to 9. So it'd be like 900, 9,000, 90,000, 900,000. It'll still go to infinity. Okay. Thirdly, then, if you have the limit as x goes to c of a ratio where the denominator is going to infinity, what's going to happen there? Well, you'll have this type we'll call L over infinity this time, right? And it'll go to 0 because you're going to have this denominator that's just getting huge. So it would be like 1 over 10, 1 over 100, 1 over 1,000, 1 over a million. And you put that into a calculator, it's like 0.1, 0.001, 0.00001. So it's getting really, really close to 0. There's all kinds of other limits, forms. You'll probably study them in more detail in Calc 2, but if you have something going to infinity plus something going to infinity, that's infinity. Negative infinity plus negative infinity is negative infinity. And two things going to infinity simultaneously, you can just take the product of their signs. So if you had something going to infinity and then something going to negative infinity, that would be negative infinity. Okay. Negative infinity times negative infinity, guess what? It's positive infinity. And so on and so forth, right? And I guess we didn't really look at when g was negative up here, but if you had something like infinity minus L, that's still going to be infinity. Try to think what else we could say. L minus negative infinity would be L plus infinity, which would just be infinity. You have to be a little careful because some of these are going to end up being indeterminate, and you'll study those in more detail in Calc 2. And the indeterminate forms are where you have a competition going on. So just be aware. Right now, our only indeterminate form is 0 over 0, but later on we'll have infinity over infinity as indeterminate. Infinity minus infinity. So there's this battle going on, you know, which one is going to win out. positive infinity or negative infinity, or are they just going to equal each other? Is it just going to be 0? You know, okay, so this is, you know, for Calc 2, but you're kind of expected to be able to handle all of these scenarios here in Calc 1. So anyways, let's look at maybe 1 or 2 from the book. Here's 44. We have the limit as x goes to 0 from the right of 6 minus 1 all over x cubed. Okay. The limit as x goes to 0 from the right of this guy right here, 1 over x cubed. Well, you can note this is L over 0, so it's going to be infinity or negative infinity. If you do a table, and we're approaching 0 from the right, you'll want to pick values like 0.1, so it'll be positive over positive. In other words, this is positive infinity. Okay. So what type do we have then? Well, the limit of 6 is just 6. So I'll have L, some number L, minus this thing, which is infinity. Okay. So with just this alone, it'll be like negative 100, negative 1,000, negative 10,000. If you put this here, it'll be like negative 9, negative 99, negative 999. In other words, this L won't make a difference. It's just going to go to negative infinity. Let's look at 45. We have the limit as x goes to negative 4 from the left of x squared plus 2 all over x plus 4. Okay. And again, we're going to kind of pick this part out. This part will just be a constant L. If you put negative 4 into there, you could do a substitution on this limit, and it will be constant L. And then we got to figure out, is this going to positive or negative infinity? So I'm picking out this particular limit. And figuring it out. So I'm approaching negative 4 from the left. So I need to pick a value like negative 4.1. If I plug that into there, I'll get a positive over a negative. So this guy right here is negative infinity. So L minus infinity form. And again, it will be negative infinity. Let's look at one more. So this is 48. And we have the limit as x goes to pi over 2 of negative 2 all over the cosine of x. Okay. So the cosine of pi over 2 is 0. So again, you have L all over 0. Okay. It's going to be infinity or negative infinity. You just have to figure out which. And in this case, I'm just going to draw sort of a little graph, and then it's coming in from the right, and then kind of figure it out that way. So if you come in from the positive direction, the cosine values will be negative. Okay, so it would be a negative over a negative. In other words, positive infinity. Okay, thanks for watching.